This is applications of Biot-Savart law. So we know the Biot-Savart law can be converted into mu naught I by 4 pi r sin alpha plus sin beta for a finite rod carrying current I at a distance r from it. Here if you want to find out a magnetic field, so by using this Biot-Savart law, we derived this equation in the last class by taking this angle as alpha, this angle as beta. So I replace this alpha and beta here with the theta 1 and theta 2. You can write alpha, beta, theta 1, theta 2, whatever you want. Now, I am going to use this formula in so many different cases. So actually that was the application of Biot-Savart law only. By using Biot-Savart law, we derived that equation. Now, suppose if there is a equilateral triangle carrying current like this, so it is carrying some current I, let the side of this equilateral triangle is A. So the first one is equilateral triangle. How to find out magnetic field at the centroid of equilateral triangle? Now, if I want to apply that formula here, first I can take a single side, any one of the side of this equilateral triangle. Now, if you know the magnetic field due to this first side, this is the second side and this is the third side. Now, if you take this first side, let me take it as X, Y, Z. I am not taking A, B, C. Why? Because I am going to find out B. That's why I am taking this as P, Q, R, X, Y, Z. So I am taking here X, Y, Z. Now, what is the magnetic field due to this side at this point? So I am taking this point as centroid as O. This is O. And to apply that formula, I need the finite length of the wire and the distance of this one I am denoting with R. And this angle, if I want to find out the magnetic field due to this wire, join this point with the both ends. First one, second one. This is alpha and this one is beta and this side is R. So I am going to find out magnetic field due to XY is equal mu naught into the current flowing through this one is I, and 4 pi, the distance from this point to this is R. I need to take only the perpendicular distance into sine of alpha plus sine beta. So I am taking this as sine alpha plus the second one is sine beta. So this is the formula to find out the magnetic field due to one side. Now what is this alpha value, beta value? Now you can see this is a complete circle and you can divide this complete circle into 3 equal parts. Total angle subscribed at the center is 360 degrees, which is divided into, this is first part, this is completely second part, this is completely third part. So 3 parts. Now if you want to find out the perpendicular distance from this one, this is one more part and this is one more part. Or this 360 degrees can be divided into 1, 2, 3, 4, 5, 6 parts. So each part is equal. So here 360 parts is divided into 6 parts. Each part is equal to 60 degrees. That means alpha is equal to 16 as beta also 60 degrees. So I can substitute this value here. Magnetic field due to XY side of this equilateral triangle is given by mu naught I by 4 pi r. This is sine 60 plus sine 16. So I am going to substitute this alpha and beta value as I got alpha as 60, beta as 16. I am going to substitute this 60 degrees, 60 degrees. Now I can write this as mu naught I by 4 pi r. Sine 60 is equal to root 3 by 2 plus root 3 by 2. So this is the root 3 by 2 plus root 3 by 2. So these are the two values. But here in this problem, this r is not given. We assumed that the distance of this centroid from this side is r. I need to convert this r into terms of a. So for this what I am going to do, I am going to take this triangle. So from the small triangle portion here, If it is R, this length is A, this length would be A by 2. And we know that in an equal triangle each side is 60. So this is the bisector angle, so bisector line. So this will be 30 degrees. Only this one is the 30. So this will be 30. So tan 30 is equal R by A by 2. 1 by root 3 is equal to R by A by 2. So R is equal to A by 2 root 3. Exy is given by mu naught I by 4 pi. R is equal to A by 2 root 3. This is A by 2 root 3 into root 3 by 2 plus root 3 by 2. 2 root 3 by 2 are simply root 3. Now you can write this 2 root 3 in the numerator. You will get mu naught I 2 root 3 into root 3 by 4 pi A. So 2 1s, 2 2's cancel here. This will come 3 times because root 3 is 3. 3 mu naught I by 2 pi A. This is the magnetic field due to one side. But how to find the magnetic field at the centroid of this equilateral triangle? To find out the magnetic field at the center of the equilateral triangle, so first let me take whether it is acting into the board or outside the board. Here, as the current is flowing from X to Y, so I am keeping my thumb in the direction of XY, and at O, the fingers are pointed outwards. So magnetic field is outwards. So magnetic field due to that XY side is outwards. Now similarly, if you take the direction of current from Y to Z, here, see the thumb is shown like this. Here field is inwards. But I don't want magnetic field outside the triangle. I want magnetic field at the centroid of this triangle. So you just change your finger like this. Don't change the direction of current. Here field will be outside. So magnetic field due to YZ also due to this magnetic field. The magnetic field due to the current flowing from Y to Z is also outwards. Similarly here, if you keep the finger like this, here field is inside. Outside the triangle field is inside, but inside the triangle field is outside. So the magnetic field due to XY, magnetic field due to YZ, magnetic field due to ZX, this is acting outside, this is acting outside, this is acting outside. All these three fields are acting outside. Magnetic field is a vector. So as it is a vector, the net magnetic field is given by, as all are acting in the same direction, we can add them directly. So this will be BXY, BYZ, BZX. But you can see the magnetic field due to this XY side, one of the side, depends upon current flowing through this one and side of the triangle, and all other constants are constant. 3 mu naught 2 pi are constant. It only depends on current and side. For this XY side, length is A, current is I. For this also length A, as it is equilateral triangle, length A, current I. This also length A, current I. So all the three sides of the triangle will produce equal magnitudes of the magnetic field. That's why we can write B net is given by 3 times of magnetic field due to each side, or 3 times of magnetic field due to XY. Why? Because we found the XY value here. So this is the XY value. So I am going to substitute this here. 3 into, this is 3 mu naught I by 2 pi A. So this will become 9 into mu naught I by 2 pi A. So this is the magnetic field at the centroid of an equal triangle. But always when these type of questions are given, in the options they will give this magnitude and they will give the direction also. Here the total magnetic field is acting outwards. So indicate with a circle at a dot at its center. The magnetic field at the center of a square of side A carrying a current I. So let me draw the diagram. So I am going to take a square here of side A. So side of this square is equal to A, and it is carrying some current in any one direction, either clockwise or anti-clockwise. Here it is carrying current in the anti-clockwise direction. So side of this one is A. Now I want to find out magnetic field at the center of this square. Once again, I am going to use the same concept. Magnetic field due to finite wire. This is a finite wire, second finite wire, third finite wire, fourth finite wire. So I am going to take this wire as first wire, second wire, third wire, fourth wire. So at point O, I want to find out the magnetic field. To find out this one, first of all, let me use this formula to find out the magnetic field due to one side. Due to this side, so I am going to take this as P, Q, R, S. So what is the magnetic field due to the finite wire PQ here? Formula is mu naught times the current flowing through this wire by 4 pi into the perpendicular distance between this center to this one. So I am going to extend draw one line here. So this will become R. So this is I am going to take R into sine of alpha plus sine of beta. So what is this alpha and what is this beta? If you know this alpha and beta, you can solve this problem very easily. Now, to find out this one, our method is wherever you want to find out the magnetic field, join that point with both ends of that finite wire. So here also, I want to find out magnetic field due to P and Q, join OP, join OQ. And you know this is totally 360 degrees. Now you can divide this into, so this angle will be alpha and this angle will be beta, and these two angles are equal. Why? Because this is A by 2, this is also A by 2, so this angle must be 45. This is A by 2, this is also A by 2, 45. So alpha is equal to beta is equal to 45. If you add 45, 45, 90, 45, 45, 90, 45, 45, 90, 45, 45, 90, total 360 degrees. It is divided into 8 equal parts. In the triangle, it was divided into 6 equal parts. In a square, 8 equal parts. So I know this alpha value, I know this beta value. Now let me substitute this one. Mu naught times the current flowing through this wire into 4 pi into. This R is no need to calculate, as it is 45, it is 90, this is also 45. So tan 45 is equal to R by A by 2. Tan 45 is equal R by this side, opposite side by adjacent side, A by 2. So this is 1. So R is equal to A by 2. Directly I can write. Otherwise, if it is total side A, half of it will be A by 2 only. So in place of R, I am writing A by 2 into sine of sine 45 plus sine 45 degrees. Now this can be written as 2 ones, 2 2's. So this will become mu naught I by 2 pi a. Sine 45 is 1 by root 2 plus 1 by root 2. So what is the magnetic field due to one of the side, that is magnetic field due to PQ is given by, you can simplify this equation as mu naught I by 2 pi a. 1 by root 2 plus 1 by root 2 will become 2 by root 2. So I am going to write 2 by root 2. So this 2 get cancelled. Mu naught I by pi a into root 2. So this is the magnetic field due to one side. But I want to magnetic field due to the entire square at its center, which is given by magnetic field due to PQ, magnetic field due to QR, magnetic field due to RS, magnetic field due to SP. Now, what is the direction of this one? First of all, whenever we are finding magnetic field, this is the magnitude of this one and what is its direction. So here, current is flowing like this. So field at point O is outwards. So I am going to keep this as outwards. But what about the magnetic field due to PQ? This is outwards. So I am going to write here outwards. Magnetic field due to QR. Keep the thumb in the direction of current and you curl the fingers wherever you need to find the direction of the magnetic field. Here it is outside. So this is outwards. This is also, here field is inwards above the square, but below the square it is outwards. So this is outwards and this is also outwards. So all magnetic fields are acting outwards only as they are vectors. Once again I am adding this. So magnetic field at the center of this one, which is equal to 4 times the magnetic field due to any one of the side, and already I found this as I found this value mu naught I by root 2 pi a, which is acting outwards. All fields are acting outwards. I am taking this as outwards. Now the net magnetic field at the center of a square, so B at O or B at center is given by 4 times of, this is the magnetic field due to one of the side of the square, root 2 pi a. So now you can cancel this as, this can be written as 2 into root 2 into root 2. So this will become 2 root 2 mu naught I by pi a. This is the magnetic field at the center of a square. Third application, magnetic field due to hexagon. Now let me draw a hexagon here. 1, 2, 3, 4, 5, 6. This is a hexagon of side A. Side of this hexagon is A. And here in the previous two cases I took this current in anti-clockwise direction. So let me take the current here in clockwise direction. Let us say current is flowing like this. Just for a change, we are changing the direction of current. And we know that in a hexagon, all sides are equal, and this will be the centroid of this hexagon. Now, how to find the magnetic field at the center of this hexagon? So, magnetic field at O, that is center of the hexagon, equal to, here hexagon consists of 6 sides. So, this is 6 times of magnetic field due to any one of the side. So, you can take this as a P, Q, R, S, T, U. So, this is a magnetic field due to P, Q here. So, by using the same concept, by using the same formula, I am going to find out the magnetic field due to one side. Here once again, to find out the magnetic field here, draw the perpendicular from that point to this one, and here totally this is divided into 6 parts, and once again this is divided into 2 more parts. So totally 360 degrees will be divided into 12 parts. So 360 degrees by 12, so each angle will be 30 degrees. So alpha is equal to 30, beta also equal to 30. So this is mu naught I by 4 pi r sin 30 plus sin 30. So this is the expression. Now what is this r value? You can see this is r value. So I need this value, this is equal to a by 2. If you take tan angle here, tan 30 degrees is equal to opposite side by hypotenuse, which is equal to a by 2 by r. So tan 30 is 1 by root 3 is equal to a by 2r. So r is equal to, this r will go this side, this is root 3 a by 2. So I am going to substitute this one, 6 times of mu naught I by 4 pi r. In place of r I am going to write root 3 a by 2. This will become root 3 a by 2 sin 30 1 by 2 plus 1 by 2, which is equal to 1. Now what are the terms that can be cancelled? 2 1 so 2 2 so 2 1 so 2 3 so, which is equal to 3 mu naught I by root 3 pi a. So this is the magnetic field due to the entire hexagon. Why? Because I am multiplying this with 6. Or even you can cancel this as root 3 root 3. This will become root 3 mu naught I by pi a. This is the magnetic field at the centroid of a hexagon. Now the fourth one, the magnetic field at the center of a regular polygon of n sides carrying current I. So here, just now we derived the expression for the magnetic field at the center of a triangle, center of a square, center of a hexagon like this. Now I am going to increase the sides of the polygon. So now I am going to take one polygon which is carrying current like this. So it has so many sides. Once again it may be 8, 10, 15, whatever it may be. So the current flowing to this one is I. Side of each polygon is A. Now I want to find out magnetic field at the center of this regular polygon. So to find out this one, I am going to use the same expression there. So first let me find out this as R, the distance of this current carrying finite wire from the center of the polygon as R, and you join this with this end and this end. this will be alpha, this will be beta. As these two are equal, so I'm going to take this as theta and theta. So both alpha and beta are equal, which is equal to theta. In all polygons, alpha is equal to beta, which is equal to theta. So here I am going to write this one. This side is R. So what is the magnetic field due to this side? So magnetic field due to one side at the center is given by mu naught times the current flowing by 4 pi into the distance of this one from the center. I want this R. So first let me substitute R only into sine of theta plus sine of theta, because alpha is equal to beta is equal to theta. Now how to find this R value? In this we can write, if it is A, if it is R, you can write this as capital R. Distance from the centroid to the one of the vertex of this polygon, I am taking it as R. Now I want this R in terms of A. So we know that this side is A, this will become A by 2. So this is opposite side, this is adjacent side. I can write tan theta is equal to opposite side A by 2 by adjacent side R. So in place of this you can write A by 2R, can also be written as R is equal to A by 2 tan theta. So in place of R I am going to replace this with A by 2 tan theta. So this is mu naught I by 4 pi into A by 2 tan theta. This is A by 2 tan theta into, this is sin theta plus sin theta, you can write 2 sin theta. Now this can be represented as, this is mu naught I by 4 pi A. This 2 tan theta will go to numerator. This is 2 tan theta into 2 sin theta. This 2's are 4 and this 4 get cancels. So the magnetic field due to one side of a regular polygon is given by, magnetic field B is given by, due to one side, mu naught times the current into tan theta into sin theta by pi A. So this is pi into A. This is tan theta into sin theta. You can say this one, in any regular polygon, suppose if you take a triangle, the total angle I divide into 6 equal parts. So this is alpha beta, here also alpha beta, here also alpha beta. So when there are 3 sides, for 3 sides I am dividing 2 pi into 6 parts. Similarly, if you take the square here, so I am dividing this into alpha beta, here alpha beta, here alpha beta, here alpha beta. So when there are 4 sides, for 4 sides I am dividing 2 pi into 8 parts. As this regular polygon has n sides, so I am going to take a n side polygon. For n sides, 2 pi angle will be divided into 2n. So what we can write, the total angle described in the center is 2 pi radians. So here I am going to write 2 pi radians is divided into 2n times of that each angle. So here let us say if it is theta 1, 2, 3, 4, 5, 6, 7, 8, this will become 8 theta. If it is theta 1, 2, 3, 4, this will become 6 theta. If it is theta, 2 pi will be divided into 2n times of theta. So I am going to write 2 pi angle described by the center is equal to 2 into n into theta. Now you can cancel 2 and 2. So theta can be written as pi by n. So here I am going to replace this one. Mu naught times the current by pi A. This is tan theta. So we can write tan of, in place of theta I can write pi by n into sin theta. So here also we can write sin of pi by n. But what is the sin theta value here? From the same triangle, you can write sin theta as opposite side by hypotenuse, that is a by 2 by r. But theta can also be as sin pi by n, which is equal to a by 2r. So you can replace this sin pi by n as a by 2r. So you can write mu naught into I by pi into a into tan pi by n into sin pi by n or sin theta is equal to a by 2r. So I can write this as a by 2r. So don't confuse between this is small r and capital R. Small r is the perpendicular distance between this point to this element, this infinite wire, and capital R is the distance from this point to the vertex of this one. So this is magnetic field due to one side of a regular polygon. How to find magnetic field due to the entire polygon? The magnetic field due to the entire polygon at the center, magnetic field at center of polygon is equal n into, why? Because while finding this one, after finding magnetic field due to one side, I am multiplying with 3 as it is having three sides. Similarly here, after finding magnetic field due to one side, I am multiplying with 4. Here also, after finding magnetic field due to one side, I am multiplying with n times the magnetic field due to one side. This is the magnetic field due to one side. So I am going to write mu naught I by pi a into a by 2r into tan pi by n. So this is the expression. Here you can see this a and a get cancels. So magnetic field due to the at the center of a regular polygon is given by, so B at O, that is center of the regular polygon, is equal to mu naught I into, this is n by pi, this is n by pi into, this is 2r, here this is 2r into tan pi by n. So this can also be written as mu naught I by 2r tan pi by n by pi by n, which can be written as n by pi here. So this is a magnetic field at the center of a regular polygon. In this expression, if n tends to infinite side, if the polygon has infinite side, see, if I want to draw a polygon like this, this is a hexagon. Similarly, if you take one more here, so if number of sides increases, completely it will become a circle. So when n tends to infinity, the polygon becomes a circle. Polygon becomes a circle here. So what is the magnetic field due to infinite number of sides of a polygon, which is almost a circle? So this will become mu naught I by 2r into tan of pi by 2 by pi by 2. So we studied this in mathematics. If n tends to infinity, this value will become 1. So this is 1. So this is a magnetic field due to the center, magnetic field at the center of a circular loop, which is equal to mu naught I by 2r. So n tends to infinity, this expression will become equal to magnetic field at the center of a circular loop. Field due to a circular current carrying loop. This is a 5 mark derivation for PUC. So here I am going to write, this is a circular loop carrying some current I in this one, where the radius of this circular coil is r. I want to find out magnitude of the axis of the circular current coil at point P, and the distance of the center to this point P, let us say this is x as it is along x axis. Now, here if I want to find out magnetic field, here also I am going to use the Biot Savart law only. So what is the magnetic field? As it is not a small element, so let me consider a small element. Why? Because the Biot Savart law can be applied for a small element only. So this is an element of length dl. So for this element, I want to apply Biot Savart law to find out magnetic field here. As it is, this is x. This distance will become, from Pythagoras theorem, this will become root over r square plus x square. So what is the magnetic field at point P? So magnetic field at point P due to the small elemental portion of the circular ring is given by mu naught I dl sin theta mu naught by 4 pi into ideal sin theta by r square. This is the expression. But what is r here? It is the distance between the small element and this point. So here small r is equal to root over capital R plus r square plus x square under root. So I can write this as mu naught by 4 pi, which is a constant. Current flowing to the small element is I. What is this dl? So it is given as dl only. What is this r value? Root over r square plus x square whole square into what is this sin theta? Theta is the angle between the element and the line joining the element with the given point. So here let me consider a small circular current carrying coil. So let us say this is a small element considered here. I want to magnify on the axis of this one. Let us say this is the axis of this one, and I want to find out magnitude at the tip of the pen here. This is the axis and this is the point P. So for this small element, I need to join this small element with this tip. This is small r. The length of this pen is small r. The length of this pen is small x, and this is radius r. So while calculating this one, what is the angle between this line joining the element with this point with this one? So here you can see the angle between this and this. When you are throwing like this and this are perpendicular to each other. So I can take theta as 90. So this will become sine 90 degrees. This is magnitude due to the small elemental portion. So now let me simplify this one. This will become mu naught I dl by 4 pi into square and root get cancelled. R square plus x square sin 90 is 1. So this is equation 1. This is the magnitude due to the small element. But in Biot Savart law, we found that the magnetic field is perpendicular to dl bar cross r bar. So dB is perpendicular to dl bar as well as r bar. Here, what is dl bar? Once again, let me take this one. This is the small element that I am considering here. Out of this entire element, entire loop, this is the small element. So this is dl, and I want to magnify at this point x. So if you join these two, this is r bar. So magnitude should be perpendicular to r bar like this, and also perpendicular to this element here. So it should be like this. So this is the direction of the magnitude here. This is the direction of magnetic field. But in case of electric field, if you want to find out electric field due to a small charge, this electric field always acts along the line joining the charge with the point. Either in this direction if it is positive charge. If it is a negative charge, it will act in this direction. But the magnetic field is entirely different. It will not act along the line joining this. It is always perpendicular to r bar as well as dl bar. So now this is dB. Now if you divide this, if you denote this with theta, and this will be the angle, you can resolve this into two components. If it is theta, this is 90 minus theta. Once again, this will be theta, and this is 90 minus theta. So if it is dB, now you can write this as dB cos theta, and this will become dB sin theta. Similarly, if you consider one more small element here of length dl, once again if you join these two, dB will act like this. This is dB cos dB sin theta. So this will be dB cos theta, this is dB, and this will become dB sin theta. As it is a symmetrical diagram, all the vertical components, that is dB cos theta components, will be cancelled out. So all dB cos theta components will be cancelled out. Cancels each other. So if you want to find out the net magnetic field due to a circular portion, so B net or B on the axis of a circular current carrying coil is given by integral of dB sin theta, because I am adding only dB sin theta components, sigma dB sin theta, dB sin theta plus dB sin like that. But this is the expression. Now substitute this dB, which is given by mu naught into current into dl by 4 pi into r square plus x square What is this sin theta? Here we have a triangle. So from this equal right angle triangle, sin theta is equal to opposite side by hypotenuse, which is given by r by root over r square plus h square from the triangle. Now what are the constants? You can bring it outside by integration into this one. So this will become mu naught into I into r by 4 pi into r square plus x square whole power 3 by 2, as it is 1, this is half. Integral of dl. What is dl minimum value? dl minimum value is 0 because it is very very small, dl becomes 0, and if it is maximum it will become 2 pi r. So the limits for here in this are 0 and 2 pi r. So this can be written as mu naught times of I into r by 4 pi into r square plus x square whole power 3 by 2 into integral dl is equal to L and L is equal to 2 pi r. So I can write 2 pi r. So you can cancel 2 pi 1s and 2 pi 2s here. The magnetic field at the axis, on the axis of the circular current carrying coil is given by, so B on the axis of the circular loop is given by mu naught times of I into this r into r will become r square by 2 into r square plus x square whole power 3 by 2. So this is the magnetic field on the axis. Now based on this one, we can find out magnetic field at different points. Now first one, what happens if you take the magnetic field at the center? So just now we found magnetic field at this point. If you want to find out magnetic field at the center, so magnetic field at the center of a loop. If you want to use this formula, I can write mu naught into I into r square never changes because mu naught is a constant. Current through this one is constant. The radius of this coil is constant. And the 2 is also this, which is constant, r square plus. Now from here to here, the distance is x. If you want to take this point here, the x will become 0. So the only difference is this will become 0 square whole power 3 by 2. So magnetic field at the center of a loop is given by mu naught I r square by 2 into r square whole power 3 by 2, 2 to get cancelled, this will become r cube. So r square and r cancel. This is a very very important expression. The magnetic field at the center of a circular loop is given by mu naught I by 2r. Now, if the coil consists of n turns, for n turns, the magnetic field at the center is given by mu naught to ni by 2r. This is the magnetic field at the center of a circular current carrying coil. Now, if the point is not nearer to this one, let us say it is far away from this at a large distance. So at a large distance, what is the magnetic field? In the first case, the magnetic field at the center, that just now we got it as mu naught ni by 2r. Second one, at a parallel point, at a large distance. Now, what happens to the formula here? So this is the magnetic field on the axis of this one. So B can be written as B is equal at a large distance on the axis of a circular loop is given by mu naught ni r square by 2 into r square plus x square whole power 3 by 2. When x is very large, large distance means x is much greater than capital R. So if you spiral on this one, x square will be very 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 high, and which is much larger than r square, or r square can be taken as 0 while adding this with r square. But in multiplication, r square remains as r square. But while adding, r square is negligible, x square is too large. So magnetic field at an infinite distance is given, not infinite distance, at large distance. At a large distance is given by mu naught ni r square by 2 into. This you can neglect here. You can take it as 0. So this will become 0. So this is x square whole power 3 by 2. So this will become x cube. Now this you multiply with 2 pi and divide with 2 pi, the equation remains as it is. So the magnitude at a large distance is given by mu naught into n into I into pi r square into, here I can write this 2 here by 2 into 2 pi will become 4 pi into x cube. So this value given as mu naught by 4 pi is a constant. This is 2 times of NIA by x cube. So this is N is the number of turns in the coil, I is the current in the coil, and pi r square is the area of that coil. And in magnetism we studied this as the product of current and area is called magnetic moment of the coil. So here you can write mu naught by 4 pi 2 into m by x cube. This is the magnitude at a large distance into a coil. That means for a bar magnet, if you take a bar magnet here of magnetic moment m and a distance x from this one on its axis, the magnitude is given by mu naught by 4 pi 2m by x cube. This is the magnetic field on the axis of a bar magnet. But you can see the current carrying coil also gives the same expression mu naught by 4 pi 2m by x cube. That means every current carrying conductor acts as a bar magnet. So the conclusion is every current carrying loop acts as a bar magnet. So we can prove it by showing this B at a large distance due to a circular current carrying coil is equal to mu naught by 4 pi 2m by x cube. Similarly, if you take the third case where x is not that much big, so close to the center of loop, that is x is much lesser than r. So in this case, how to write magnetic field here? Magnetic field at a small distance is given by mu naught ni r square by 2 of r square plus x square whole over 3 by 2. So this you can write mu naught ni by 2. Multiply this with r, divide with r, you will get this r will come here. This will become mu naught ni r cube by, this is r square plus x square whole power 3 by 2. Now this can also be written as mu naught ni by 2r. This is the magnitude at the center of the circular loop into. So the remaining terms of this is r cube by r square plus x square. You can bring this r cube down, or you can also write this as 1 by r square plus x square by r square whole power 3 by 2. So you can see the denominator r square plus x square whole power 3 by 2. This is r square whole power 3 by 2 r cube and close to this to r cube only. So now this can be written as mu naught ni by 2r. This is r square plus x square by r square whole power minus 3 by 2. So this can be written as mu naught ni by 2r. This is r square by r square is 1 plus x square by r square whole power minus 3 by 2. If as x is very small, x square by r square will be negligible, and this is in the form of in binary expression 1 plus x whole power n can be written as 1 plus nx. So this we can write if x is very small. Suppose in any expression 1 plus x whole power n will become 1 plus nx if x is much lesser than 1. So this is from binary expansion. So binary approximation you can write this is 1 plus this as x whole power n. As it is very small, you can write this as magnetic field at a small distance is given by mu naught ni by 2r, that is magnetic field at the center, into 1 minus 3 by 2 into x square by r square. This is the magnetic field on the axis when it is very close to the center. Discussed in this case, every current carrying loop acts as a bar magnet. Let us say this is a current carrying loop, carrying current in the clockwise direction. So current is flowing in the clockwise direction. We can apply Ampere right hand rule to find out the direction of the magnetic field due to this circular current carrying coil. Here, just like when we are holding a current carrying conductor on our right hand such that the direction of the current is in the direction of the thumb, the curled fingers will give the direction of the magnetic field around the current carrying coil. This is the Ampere's right hand rule to find out the direction of the magnetic field due to a straight current carrying conductor. But the same expression, the same rule can also be applied for a circular current carrying coil also. The only difference is here current is flowing along a straight line and a magnetic field is circular around the current carrying conductor. But if the current is flowing in a circular path, the magnetic field will be straight along a straight line. So here I am going to use the same thing here, but instead of this current, let us say current is flowing in the direction of the curled fingers. The magnetic field is along the thumb indicated by your right hand. So when the current is flowing in clockwise direction, here the thumb is indicating inwards. So this is into. So the magnetic field is into the board. So B is inwards. Similarly, if the current carrying conductor or loop is carrying current in the anti-clockwise direction, so this is the direction of the current. Here you can apply the same right hand rule by keeping your curled fingers in the direction of the current. The thumb will give the direction of the magnetic field. So here field is outwards. So this is B. So magnetic field is outwards. Okay. Now, as we said, every current carrying loop acts as a bar magnet. A bar magnet will have two poles. One is the north pole, or the other one is south pole. Here, a current carrying conductor is carrying current in the clockwise direction. So, if you watch from this side, how the face of this coil act, whether it acts as a north pole or south pole. Here, as the current is going like this here current is moving in this direction. If you add these two, so this is the direction of the face. That is, the current carrying coil carrying current in clockwise direction acts as a south pole. This will act as a south pole. Similarly, if you take this current carrying coil which is carrying current in the anti-clockwise direction, so here the current is flowing down and here the current is going up. So it is easy to remember that this current carrying coil carrying current in the anti-clockwise direction act as a north pole. Application: magnetic field due to a circular arc. Here I am going to take a magnetic wire carrying some current I, and I want to find out magnetic field due to this circular current carrying wire. So here I want to find out magnetic field at the center of this circular current carrying arc, circular arc. Let the radius of this one is r. To find out the magnetic field, here I cannot use a direct formula here. I can use a Biot Savart law only. So let the angle made by this entire arc at the center, let us say this is a theta. So this angle I am denoting this as a theta. This angle is theta. Now if you divide this into this one to equal parts, I need to take a small elemental portion of length dl here, because the Biot Savart law can apply only for a small elemental portion. Now if I join this one here with the center So this is a small elemental portion of length dl. So let us say this angle here is alpha, and this angle I can take it as d alpha. So what is the magnetic field at point O due to this small element here? So I am going to write dB is equal mu naught by 4 pi I into current flowing through this wire is I, arc is I, into dl into sine theta by r square. Here what is r square? R is the distance from small element to this point, which is given as capital R. So directly I am going to substitute this as a capital R square. What is the sine angle here? Sine angle is the angle between the element and the line joining this element with the point. So this is 90 only. For this it is 90. So I can take a theta as 90. So dB is given by mu naught by 4 pi I into dl into sine 90 is 1. So I am directly writing this is theta 90, sine 90 is 1. So dB can be written as mu naught by 4 pi current I. What is that dl? So this is a small arc here. We know that arc length is equal to radius into angle subtended by the torque at the center. So the arc length dl is given by r into this small angle d alpha. So I am going to write this as, in place of dl I am going to write r into d alpha by r square. This and this get cancelled. So final expression to find out the magnetic field at the center would be a small part of a arc is given by mu naught by 4 pi I by r into d alpha. This is equation 1. Now if I want to find out magnetic field due to the entire arc here, integrate this small element, net magnetic field due to arc is given by integral of dB. So this is integral of, this is dB, which is equal to mu naught I by 4 pi r into d alpha. Now what are the constants? Bring them outside, and alpha is, d alpha is the variable. That means I need to take the lower limit and upper limit in terms of angle only. So what is the minimum angle of alpha here? This angle minimum value will be, if you take this strip somewhere here, minimum angle is 0 and the maximum angle is theta. So the limits are 0 and theta here. So bring the constant outside, mu naught I by 4 pi r integral d phi from the limits 0 to theta. So this will be mu naught I by 4 pi r integral d alpha is called integral of d, this is alpha with the limits 0 to theta. So this will be mu naught I by 4 pi r theta minus 0. So the magnetic field due to an arc at its center is given by, this is mu naught I by 4 pi r into theta. One more important derivation. Why? Because in some problems we need to take some arcs here. Suppose if theta is equal to 360 degrees, so then this arc will become a circle. Suppose if theta is equal to 2 pi radians over r 360 degrees, B will become mu naught I by 4 pi r into 2 pi. This pi and pi get cancelled, 2 and 2 get cancelled, which is equal to mu naught I by 2r. This is the magnetic field due to a circle at the center of a circular loop. Similarly, if theta is equal to 90 degrees, that is pi by 2, so B due to this is complete circle, this is quarter of a circle, because 90 means this arc will be like this, carrying current like this. So this will become mu naught I by 4 pi r into pi by 2, pi and pi get cancelled, mu naught I by, this will become 8r. This is 1/4 of this one. Now if it is theta is 180, that is for semicircular, if theta is equal to 180 or pi radians, then B will become mu naught I by 4 pi r and this will become pi only, this pi and pi get cancelled, mu naught I by 4r. This is the magnetic field due to a semicircular coil carrying current I. But every time when you are writing these magnetic fields, this is the magnitude of the magnetic field and we need to indicate the direction also. Here, as the current is flowing in the direction of the curved fingers, the field is into the board. Here we have to represent this with into here. Similarly for this also, as I am drawing the current in this direction, for every expression I need to indicate the direction of the magnetic field into the board.